You know that feeling you sometimes get when you're machining softer metals, like aluminum?
I mean,
It feels like you're wrestling with the machine almost, trying to get a clean profile.
definitely fighting it.
And you end up fighting vibration, the finish isn't quite right.
And wasting material, too.
Exactly. It's a familiar headache, isn't it, for anyone doing this kind of work?
It really is. And, often the root of that frustration, it comes down to something that seems simple.
What's that?
The cutting tool you choose.
Ah, seems straightforward, but it's not.
No, it has this huge ripple effect on, well, everything. Your whole machining outcome.
That's actually exactly what we want to dive into today, really zeroing in on why picking the right cutting tool is so critical.
Especially for aluminum profile machining.
Right. Getting that accuracy, that stability. This isn't about just grabbing any old bit off the shelf.
No way.
Making a smart tool choice here is like your express lane to getting better parts.
Less scrap.
And just a much smoother process overall.
Precisely. And it's more than just the first cut.
Yeah.
We're going to unpack the key things.
It's like the tool material itself.
Exactly. The material, the actual design, the geometry, we call it.
Okay.
Whether adding a coating gives you an edge.
Ah, coatings. Important.
Very. And also how you think about that balance, cost versus performance.
This smart trade-offs.
Right? Knowing these factors helps you make informed choices,
Yeah.
puts you back in control of the results.
Because, yeah, nobody wants to deal with those gummy aluminum chips,
Ugh, the worst.
clogging everything up, or that built-up edge that just ruins the finish.
Or tools that just, wear out way too fast.
Exactly. So this deep dive is really about arming you with the knowledge to avoid those common pitfalls.
So you can produce higher quality parts.
And more efficiently, too.
Yeah. Now, for this discussion, we've looked at various insights, specifically focusing on profile machining.
With aluminum, right?
With aluminum, yeah.
Yeah.
Understanding its specific quirks.
Right.
Our goal is really to pull out the essential stuff.
The nuggets of wisdom.
Exactly. The key takeaways that really show what matters when you're there, making that tool choice.
Okay, so the mission is pretty clear then. We want to equip you, the listener, with actionable insights.
For picking the right tools for aluminum profiles.
Going beyond just general tips and getting into the specifics, the things that really drive accuracy and stability.
Sounds good.
All right, let's dig in. Why is tool selection so fundamental? Why start there?
Well, it's the bedrock, really. The tool is literally where the rubber meets the road, or, where the tool meets the aluminum.
It's the point of contact.
It is. And it directly dictates the forces involved in the cut.
Okay.
How much heat gets generated, how well those chips are controlled and removed.
And vibration, too.
And the level of vibration, absolutely.
And all of those things connect directly back to what we actually want, right?
Exactly.
Parts that are dimensionally accurate,
Spot on.
a great surface finish, and a process that feels stable, not like it's about to fly off the rails.
Especially with a material like aluminum, which can be a bit temperamental, as you said.
Yeah, it's soft. It can be sticky.
Precisely. That inherent softness and its tendency to want to stick to the tool, that makes it really susceptible to problems if you use the wrong tool.
How so?
Well, think about it. If your tool isn't sharp enough, or maybe the angles are wrong,
Yeah.
it can end up sort of smearing the aluminum instead of cutting it cleanly.
Leading to bad dimensions and rough finishes.
Exactly. And furthermore, a tool that isn't quite right increases the cutting forces.
Okay.
And that extra force can introduce vibration, like you mentioned, and even affect how securely your part is held.
So the tool choice impacts work holding, too, especially with aluminum.
They're definitely linked, yeah, particularly with aluminum's characteristics.
Okay, so lesson 1, grabbing just any general purpose tool off the rack, probably not the smartest move for aluminum profiles.
You are spot on. I mean, sure, a general purpose tool might cut aluminum, but it very often leads to exactly those headaches we talked about.
Gummy chips.
Gummy chips that don't clear out, built-up edge BUE, where the aluminum actually welds itself to the tool tip.
Ruins the cut.
Totally. And you end up with a lousy finish. That's why using tools specifically designed for aluminum is, well, highly recommended.
For efficiency and clean results.
Exactly.
All right, so what are some of these specific recommended tool types we should be thinking about?
Okay, so for simple straight cuts, like on aluminum extrusions,
Yeah.
carbide saw blades are often an excellent choice. But crucially, they need tooth designs made for non-ferrous metals.
Not just any carbide saw blade.
Right. Those specific designs minimize material deformation, give you cleaner cuts.
Makes sense.
And depending on the job, you might look at a positive tooth angle.
Which is like a sharper scoop needs less force.
Kind of, yeah. Often good for softer stuff.
Right.
Or sometimes a negative tooth angle might be better for other applications.
Okay, so specialized carbide saws for straight cuts. Got it.
Right.
What about more complex shapes, like with CNC machines?
Yeah, for CNC profile machining in aluminum, carbide end mills are generally the go-to, the workhorse.
Because they're harder.
Much harder. And way more wear-resistant than, say, high-speed steel HSS.
Right.
And that hardness means you can run faster, higher speeds and feeds.
Which means faster production.
Exactly. But when you choose carbide end mills for aluminum, there's some key design features to look out for.
Okay, like what? I think I read somewhere that fewer flutes are better.
That's a big one, yes. Fewer flutes, usually just 2 or 3, means more space between the cutting edges.
The chips?
For chip evacuation, yeah. Absolutely critical with aluminum because it makes those relatively big, sticky chips. You need room for them to get out.
Makes total sense. Avoid clogging.
Right. And you'll also see end mills, especially 3-flute ones, with what's called chip breaker geometry.
Chip breakers, what do they do?
They're little grooves or features on the cutting edge designed to break up those long, stringy aluminum chips.
Into smaller, manageable pieces.
Exactly. Makes them much easier to evacuate from the cutting zone. Think of it as creating, like, better escape routes for the chips.
Clever. Okay, fewer flutes, maybe chip breakers. What else matters for these end mills?
Sharp cutting edges. Absolutely paramount for aluminum.
Why sharp specifically?
You need that clean shearing action. It reduces the cutting forces and prevents just pushing the metal around.
Got it.
And polished flutes are also a good feature. That smooth surface reduces friction.
Less slicking.
Less sticking helps prevent that built-up edge we talked about.
Okay, now you mentioned high-speed steel, HSS. Where does that fit in with aluminum? Is it still used?
It can be, yeah. HSS tools are still a viable option for maybe lower speed jobs.
Like drilling or tapping?
Drilling, tapping, simpler profiles sometimes, especially if the initial tool cost is a really big driver.
So, budget-conscious choice.
Pretty much.
Yeah.
HSS has decent toughness, which is good sometimes, but it just wears out faster than carbide,
Right.
particularly at higher speeds.
Right. And then at the other end of the spectrum, PCD.
Ah, yes. PCD, polycrystalline diamond.
Sounds expensive.
It is the premium option, definitely. It's the top tier for high-volume, high-speed work.
Especially with certain aluminum alloys.
Yeah, especially the more abrasive aluminum alloys. PCD's wear resistance is just outstanding.
Off the finish.
Usually gives you a superb surface finish. But yeah, the initial cost is significantly higher than carbide or HSS.
So it really boils down to the specific job again, doesn't it?
Absolutely.
The precision you need, how many parts you're making.
Production volume, yeah. And what your machine can actually handle.
Right. So there's no single best tool.
Nope. No one size fits all. It depends on the operation: cutting, milling, drilling, the precision required, the volume, and your machine's capabilities.
Okay, that clarifies the tool types and materials.
Yep.
Let's talk about coatings now. Are they just like an optional extra? Or do they really make a difference with aluminum?
Oh, they make a huge difference with aluminum. Skipping coatings,
Yeah.
they can often be, like we said before, penny-wise and pound-foolish.
Oh, okay.
I mean, sure, an uncoated tool might manage for, very light cuts or super low volume.
But generally,
Coatings give you significant performance boosts that are particularly valuable when you're machining aluminum. They directly attack those common problems.
like the tool wearing out too fast?
That and the big one. Aluminum sticking to the cutting edge, built-up edge.
Right. So what are these coatings actually doing? Are they like armor for the tool?
That's a great way to think about it, yeah. They enhance the tool in a few key ways.
Such as?
Well, they increase the surface hardness, making it more resistant to wear, especially abrasive wear from aluminum.
Okay, harder surface.
They also drastically reduce friction and that tendency for the aluminum to stick. That's lubricity. Super important for preventing BUE.
Makes it slipperier.
Exactly. And they improve overall wear resistance, plus they can act as a thermal barrier.
Protecting the tool from heat.
Yeah, protecting the underlying carbide or HSS from the cutting heat.
Wow, okay. That sounds like it directly addresses the aluminum challenges.
Absolutely. That reduced sticking, the lower friction.
Yeah.
It's critical for aluminum.
So specific coatings we should look for.
Yeah, things like tin titanium nitride, that's a common gold-colored one.
Okay.
Tifcan titanium carbonitride, Alton aluminum, titanium nitride, or even specialized low-friction ones like DLC,
DLC.
diamond-like carbon, they all create a much slicker surface.
So the aluminum just slides off, doesn't build up,
Exactly. Promotes better chip flow away from the cut zone.
which leads to cleaner cuts, better finishing.
Better finishes, yeah.
Yeah.
For a lot of aluminum jobs, tin is good all-around choice, good balance of hardness and low friction.
And I guess that extra hardness and wear resistance means the tools just last longer.
That's a major benefit, yes.
Yeah.
The coating acts like that protective layer.
So fewer tool changes.
Fewer tool changes, which means less downtime, and it significantly lowers your overall tooling cost in the long run.
Even if the coated tool costs more initially.
Right. Plus, that thermal barrier helps too, especially if you're pushing speeds in high-speed machining, stops the tool material degrading from heat.
Okay, so it really sounds like the benefits, longer life, maybe faster cycle times, better part quality, often justify that initial investment in a coated tool.
That's precisely the calculation you need to make. Factor all that in, and often the coated tool comes out cheaper per part produced.
Right, the cost per part. Okay, so materials, types, coatings, check. Now let's get into the actual shape of the tool, the geometry. That can't just be random.
Oh, absolutely not. Tool geometry is, well, it's paramount.
Even with the right material and coating.
Even then, yes.
Yeah.
The wrong geometry can still cause you all sorts of grief.
Like vibration.
Vibration, poor chip evacuation chips, packing up in the cut rough surface finishes, the actual shape of the cutting edges, the overall design.
It dictates how it cuts.
It dictates how effectively it cuts, how well it manages the chips, and how stable the whole process is.
Okay, so for aluminum profiles, what are the key geometric features we should be paying attention to?
Number one for aluminum, sharp cutting edges. Really sharp.
Why is sharpness so critical?
Because aluminum is relatively soft, you need a clean shearing action. Sharp edges reduce the cutting forces needed, minimize material deformation.
Okay, sharp edges. What else?
High helix angles on end mills,
Eh.
usually like 35, maybe up to 45 degrees.
And the helix angle is?
It's the angle of the fluid as it spirals up the tool. A higher angle acts like an auger, really helping to lift and eject the chips efficiently.
Pulls the chips up and out. Crucial for aluminum.
Vital. Prevents that chip packing.
Got it. High helix angles. What other geometry points?
We mentioned polished flutes earlier with coatings, but even uncoated polished flutes help.
Reduces friction again.
Reduces friction, aids chip flow, helps prevent aluminum sticking or welding to the
Makes
tool.
sense. And angles, like rake and clearance.
Yep. Positive rake angles are often good for aluminum. Think of it as a sharper scoop.
Requires less force.
Generally, yeah. Better for softer materials. And then you need the right clearance angle behind the cutting edge so the tool cuts cleanly without just rubbing on the part.
Okay. And we did touch on the number of flutes before. Remind me why fewer is often better for aluminum end mills, geometrically speaking.
Right. So typically, 2 or maybe 3 flutes are preferred for roughing or general milling in aluminum.
And the geometry reason is?
More space. With fewer flutes, there's physically more room in the channel between the cutting edges.
For those bigger, stringier aluminum chips to get out.
Exactly. Maximizes that chip evacuation space.
Okay. And those chip breaker designs, how do they fit into the geometry picture?
So chip breaker geometry means specific grooves or features ground onto the cutting edge itself.
Designed to do what?
Designed specifically to break those long, stringy chips into smaller, more manageable pieces.
Much better for chip control.
Way better. Especially more aggressive cuts. Prevents chips tangling up or getting recut.
Nasty. Okay. And back to the carbide saw blades for cutting extrusions. Any specific tooth geometry there?
Absolutely. Blades for aluminum need specific tooth shapes.
Not just the number of teeth.
No, the actual grind of the tooth, those positive or negative rake angles we mentioned.
Yeah.
It all has to be engineered to cut aluminum cleanly.
Without grabbing the material.
Without grabbing and without creating excessive burrs on the cut edge.
Right, minimizing secondary finishing.
Exactly.
So it really sounds like you need to consciously match the tool's geometry to the material aluminum in this case, and also the specific operation you're doing.
Precisely. You wouldn't use the same geometry for drilling as you would for high-speed milling.
So maybe a chip breaker and mill for milling to handle the chips.
Right.
And a specific saw blade design with the right tooth grind for clean cuts on extrusions.
You got it. The right geometric features are just crucial for getting clean cuts, good finishes, and efficient production overall.
This is all incredibly useful, but I can almost hear some listeners thinking, yeah, these specialized tools, specific geometries, coatings, They can add up, right? The price tag can be higher.
Definitely can have a higher initial price, yes.
So how do we manage that? How do we find the right balance between that upfront cost and getting the performance and tool life we need? It's really tempting to just grab the cheapest option sometimes.
It is tempting. But, like we've been saying, choosing the cheapest tool up front can very often lead to much higher costs down the line.
Okay.
That's why it's so important to think strategically. Focus on the total cost of ownership.
Total cost of ownership? TCO.
Or even better, think about the cost per part you produce.
Ah, okay. Looking beyond just the purchase price.
Exactly. You need to evaluate the tool's entire lifespan,
Hmm.
how many good parts it makes.
Right.
Factor in any reduction in cycle time it gives you because it can run faster or more efficiently.
Less machine time per part?
Yep. Think about its impact on part quality, fewer rejects or less rework needed.
That saves money too.
Big time. And consider any reduction in machine downtime because you're not changing tools as often.
Right. Less stopping and starting.
When you look at all those factors, often that higher initial investment in a quality-appropriate tool actually leads to greater savings overall.
So how do we actually put that TCO thinking into practice?
Well, first, try to get a realistic estimate. How many good parts should this tool make before it wears out?
Okay.
Then, calculate the machine time saved if a better tool lets you run, say, 20% faster.
Right. Quantify the time savings.
And don't forget the cost of that downtime, the time spent, changing a cheaper tool more frequently. What's that worth?
Good point. It all adds up.
It really does. When you look at that bigger picture, the tool that lasts longer and performs better often wins out, even if it costs more initially.
So investing in those higher quality tools, the right carbide grade, the beneficial coatings, that's often the smarter financial move in the long run.
Absolutely. The extended life, the better performance. They directly lower your cost per part.
Plus fewer scrapped parts, less rework.
Adds to the savings, exactly.
Okay, besides choosing quality tools, what else helps find that sweet spot between cost and performance?
Optimizing your machining parameters. That's critical.
Don't just guess the speeds and feeds.
Please don't. Start with the tool manufacturer's recommendations. They know their tools,
Good starting point.
definitely. But then, fine-tune them. Adjust the speeds, feeds, depth of cut for your specific machine, your setup.
To get the most out of the tool without killing it too fast.
Exactly. Maximize material removal, but preserve tool life. It's a balance.
And coolant. We mentioned it, but it feels super important for aluminum. Worth stressing again.
Cannot stress it enough. Proper coolant or lubrication is absolutely non-negotiable with aluminum.
Why so critical?
It does so much.
Yeah.
Reduces heat dramatically, minimizes friction, helps prevent that built-up edge,
Flushes the chips away too.
flushes chips away effectively, and all of that significantly extends the life of your tool.
So good cooling is basically protecting your tool investment.
You got it. Maximizing the return on that investment.
Okay. And lastly, what about just how we handle and manage the tools themselves? Does that impact the cost-performance equation?
Oh, definitely. Good tool management practices are essential.
Like what?
Like regularly inspect your tools. Look for wear, chipping, any damage.
Don't wait until it breaks mid-cut.
Exactly. Replace them proactively, based on performance, or maybe after a set number of parts or hours. Don't wait for disaster.
Tense.
Also, keep your tool holders clean and well-maintained. Make sure your whole machine setup is rigid and running smoothly.
Little things add up.
These seemingly small steps, they can have a surprisingly big impact on tool life and your overall machining efficiency.
Okay. So it really boils down to taking that holistic view, doesn't it?
Yeah, a comprehensive look.
Focusing on that total cost of ownership or cost per part.
Right.
Optimizing the whole process parameters, coolant, tool management.
That's how you make strategically sound tooling choices. Investments, really.
Investments that boost performance and profitability.
Precisely. It's about looking past that initial price ticker and seeing the long-term value.
Okay, great stuff. So just to quickly wrap up the key points here,
Yeah, let's summarize.
we've really established just how critical selecting the right tool is for aluminum profile machining. It's foundational.
Absolutely.
We looked at the importance of the tool material, choosing between carbide, maybe HSS, maybe even PCD, depending on the job.
Right, matching the material to the demands.
We explored how coatings aren't just bells and whistles. They actively fight BUE, reduce friction, and extend life.
Huge performance enhancers for aluminum.
And we detailed the crucial role of tool geometry, sharp edges, high helix angles, polished flutes, the right number of flutes, chip breakers.
All designed to cut aluminum cleanly and efficiently.
And finally, we talked about that strategic approach to cost versus performance, thinking TCO, cost per part.
Balancing initial spend with long-term value.
Okay.
Yeah. Optimizing everything around the tool
Exactly. It's about understanding how all these pieces fit together,
so you can make those informed decisions.
leading to more accurate parts, more stable processes.
And more cost-effective machining in the end.
Right. So, thinking about everything we've discussed, here's a final thought for you listening.
Okay.
Considering all these factors, material, geometry, coating, cost, what's maybe one immediate change or adjustment you could make?
In your own tooling selection
Yeah.
or your process?
Yeah. One thing that might yield the biggest improvement when you're next machining aluminum.
That's a good question to ponder. Because remember, the right tool, it's not just a cost center.
Yeah.
It's truly an investment in precision and in efficiency. How are you currently evaluating that investment in your own operations?